Good morning. We are going to start on lecture number 19 for electric drives course. We had already seen the single phase fully controlled converter fed separately excited DC motor drive. The salient points that we mentioned in that particular case where fully controlled or full converter fed DC motor drive. So the salient points that we mentioned in that particular case, where one is we are going to have negative voltage excursion. So there will be negative voltage excursion in VA. So the overall voltage we get will be diminished. That is, the positive voltage minus negative voltage will be the average voltage. So the overall voltage will be diminished as alpha increases. And the second point that we said was because when alpha is greater than 90, we are going to have average voltage to be negative, 2 quadrants of operation is possible. 2 quadrant operation is possible. So the 2 quadrants basically are going to be first and fourth quadrant. And in the first quadrant, it will be motoring. We are going to have motoring corresponding to first quadrant, whereas regenerative braking corresponding to fourth quadrant. But in regenerative braking also, we have to actually make alpha greater than 90 and EB has to be reversed. Both these things need to be done and the magnitude of EB has to be greater than the magnitude of VA. This has to be adhered to. Only then it is going to work properly in regenerative braking. The third point we mentioned was we are going to have a discontinuous conduction possible. So discontinuous conduction can happen when the torque demand is low. So IA will be low. So if IA is low and torque demand is low, we are going to have discontinuous conduction. And under this condition, speed regulation will be poor. That is, the drop in the speed is going to be much more than what we see in continuous conduction. This is because we are going to have, first of all, reduction in speed due to increase in torque. That is the inherent characteristics of the DC motor itself, separately excited DC motor itself. This is point A. And point B, we are going to see generally the negative voltage is going to increase. Negative voltage in VA is going to increase. Negative voltage portion. So overall VA comes down. So this is one of the reasons why the speed regulation is going to be pretty poor. And that is the reason this is why additional inductance may be included. Additional inductance in addition to inherent inductance LA may be included just to ensure that continuous conduction is maintained. So this may be included in the armature circuit. Another thing that may be done is that we will ensure that TE demand does not go below maybe 20% or 40% of TFL, full load torque. So this should not go below certain value so that at least there will be certain amount of current that is being drawn by the motor. So much so for single phase full converter. Now let us go over to single phase semi converter. So we are going to venture into single phase semi converter. So let us try to look at single phase semi converter. So in single phase semi converter, we are going to have two diodes and two SCRs. So the circuit is going to be somewhat like this. On the top, we have two SCRs. And at the bottom, we are going to have two diodes. So if I may call this as T1, let me call this as D4. And if I call this as T3, let me call this as D2. And then we are going to have the circuit completed with the separately excited DC motor drive being connected at the DC terminals or DC link at the output terminals. And we are going to have our supply voltage here. So I have to show the supply voltage somewhat like this. So this is A and this is going to be B. So what we see normally in a single phase semi converter is we are going to see that if the motor is already running, this is going to be the back EMF and we are going to have the rotation in this direction. Now, when there is positive half cycle, we are going to have plus here and minus here. And we are going to have, let us say T1 is fired at a particular point. Then we are going to have the current flowing from A through T1. And it is going to flow like this. And this will flow like this through the DC motor drive and return through the diode. So this is going to return through diode D4 and then it is going to go ahead like this. Okay. Now, when this is happening, let me just draw the waveform simultaneously. So this is omega t and this is going to be the supply voltage what we have. Okay. And let us say the rectified voltages during the negative half cycle is somewhat like this. And I'm going to fire T1 at this point. So this is going to be alpha and I am firing T1 at this point. And along with T1, I am assuming that D4 is also conducting. So T1 and D4 start conducting from here. So when omega t is pi, at this point, we are going to see that because D4 is functioning like a short circuit, so I can assume that this is a short circuit. Because it's a short circuit, this point B will come over here. So I'm going to have VAB as the voltage across D2. So at omega t equal to pi, D4 is already a short circuit. So due to this, we are going to have D2 is having voltage VAB across itself with A at the cathode. So if you look at VAB, VAB is going to be negative once the reverse half cycle starts. In the reverse half cycle, I'm going to have plus here and minus here. So B is going to be positive and A is going to be negative. So this is going to have the voltage with positive at the anode of D2 and negative at the cathode of D2. So D2 starts conducting. So once D2 starts conducting, what is going to happen is we are going to have this entire leg actually becoming like a short circuit. So we are going to have the current which is flowing basically is going to flow somewhat like this. This is going to circulate itself like this. So through T1, D2 and the separately excited DC motor drive. So if I may call this portion, entire thing as VA. Now I'm going to have VA to be 0. So beyond pi, VA will be 0. So if I actually draw what is VA, so the armature voltage until here, this will be the voltage. And after that, I'll be firing T3 only at pi plus alpha. So T3 will be fired only at pi plus alpha. So T1 and D4 will conduct only until pi. And after that, I'm going to have 0 voltage from here to this point. And after that, again, I will see that once T3 and D2 conduct together, once T3 is fired, I'm going to have the rectified portion of the negative half cycle directly coming up. So this shaded portion is going to be VA. So in that sense, we are not going to have any negative voltage excursion at all in our armature voltage. So the current will face less opposition. It is not going to really have more opposition at all. So if you look at the current, if it is continuous current, I'm going to have, if I say that this is the back EMF that I'm having, then the current is going to reach its maximum value somewhere here. So this will be the kind of current I will be seeing. Then it will be coming down. And again, I will see a current going up and coming down and so on. So this is the way IA is going to be. So this is IA. So if I try to look at what kind of supply current I am seeing in this particular case, the supply current, let me first of all mention the different points in the x-axis. So this is going to be alpha, this is going to be pi, and this is going to be pi plus alpha. And I'm going to have 2 pi at this point. So this is going to be 2 pi. So if I try to look at the current is probably going to increase from certain value like this. And then it reaches certain value. Please note that the value at omega t equal to pi will be slightly higher than omega t equal to alpha because the current is further coming down before it is reaching this pi plus alpha point. But beyond this, the current is just simply circulating within itself. You don't even see anything circulated from the supply side. So the supply current is going to be 0 for this portion. And again, it will increase from here and then it will reach certain value at 2 pi. So this is going to be the supply current what we see. So this will be the supply current what we see. Now, if I assume that I am going to neglect whatever is the ripple in the current and I'm going to show it somewhat like this. So this is going to be whatever is the average IA value. Similarly, this will be the average minus IA value. I should be able to write whatever is the RMS current on the supply side. if I try to write, I should write it as from alpha to pi, I have a current of Ia square d omega t. And I have to average it over pi and take the square root of that. That is what is the RMS side supply current. Supply side RMS current. So this is going to be Ia multiplied by pi minus alpha divided by pi square root. So this is going to be the RMS current which is seen on the supply side. And one more thing we'll have to say is, if I am drawing this current as ripple-free current, let me erase this completely and try to draw it as a ripple-free current. So I'm going to have this as my current. So this is going to be the current. Similarly, on the negative side also, I am going to have this as the current. So this is going to be the current. Now, when I draw the fundamental component of this current, which will be sinusoidal, if you try to derive it using Fourier expansion, it will come out to be somewhat like this. It will be a sinusoid with its zero crossing somewhere in the middle. So from 0 to alpha, if I look at it, the zero crossing of the fundamental current will be at half the distance between 0 and alpha. So that is going to be alpha by 2. So we will have the displacement of fundamental component of current from the fundamental component of voltage to be alpha by 2. So this will be the displacement between the fundamental component of voltage, that's zero crossing of the fundamental component of voltage, and zero crossing of the fundamental component of current. So displacement power factor, which is defined as cosine of the angle between the fundamental component of current and fundamental component of voltage, that is going to come out to be, in the semi-controlled converter case, it will be cos of alpha by 2. This is how it is going to be as far as the displacement power factor is concerned. And RMS current is going to be, supply side RMS current is going to be this. And if you look at what is the kind of average voltage we are getting, this is starting from alpha and it is going until pi, and it has to be averaged over pi. So I should say VA average is going to be starting from alpha until pi Vm sine omega t d omega t. And it has to be averaged over pi. So if you calculate this, we are going to have Vm by pi, and sine omega t, when you try to write, it should come out to be cos alpha minus cos pi. And cos pi is minus 1. So it will be Vm by pi divided by pi 1 plus cos alpha. This is going to be the average voltage. And if you may recall, in single phase full converter, VA average was 2 Vm by pi cos alpha. So clearly for a given alpha, the full converter VA, if I may call this as VA full, and if I may call this as VA semi. So for a given alpha, I'm going to have VA semi greater than VA full. And also one more thing you might like to observe in this particular cases, this is the kind of current we have drawn for the supply side for the semi-converter. But if I try to draw the supply side current for the full converter, so this is IS for full converter. If I try to draw, it will start from alpha and it will go until pi plus alpha. And from pi plus alpha, it will go until 2 pi plus alpha in the negative side. So this will be IA and this will also be I. This is the way the conduction is going to be. And the devices that we see in semi-controlled converter, we said T1 and D4 conduct here, whereas in fully controlled converter, the D4 will go until here, until pi plus alpha. But in semi-converter, we are going to have T1 and D2 conducting here. And we are going to have T2 and T3 and D2 conducting here from pi plus alpha until 2 pi. So we are going to have, again, if I see from 0 to alpha, we are going to have T3 and D4. So if I write explicitly what is conducting where, I should say in semi-converter 0 to alpha, I'm going to have T3 and D4. From alpha to pi, I'm going to have T1 and D2. And from pi to pi plus alpha, I'm going to have T1, alpha to pi T1 and D4, and pi to pi plus alpha, I'm going to have T1 and D2. That is both of them in the same leg. And from pi plus alpha to 2 pi, I'm going to have T3 and D2, because this device and this device, which will involve the supply, these are going to be the conducting devices for different intervals. Now, in full converter, in fully controlled converter, if I try to calculate what is the IRMS, so full converter IRMS is going to be IA square d omega t, which is starting from alpha to pi plus alpha, and I have to average it over pi, and then I have to take the square root of this. This will turn out to be IA. So the RMS current seen from the supply side for full converter is going to be higher as compared to what is the kind of RMS current I look at for the semi-converter. The semi-converter RMS current is going to be smaller and fully controlled converter RMS current is going to be larger. So this is the way it is going to work. And if I look at the fundamental component of current, if I try to draw the fundamental component of current for this, the fundamental component of current will be like this. This is how it is going to be. So the fundamental component of current will be displaced in a fully controlled converter as compared to the fundamental component of voltage by an angle alpha. So I would say again, as a comparison, if I try to write semi-converter and full converter. If I try to write what is VA in continuous conduction, this is going to be Vm by pi multiplied by 1 plus cos alpha, whereas here it is going to be 2 Vm divided by pi multiplied by cos alpha. Okay, so this is going to be the case corresponding to VA. Then if I try to look at what is the kind of current IRMS I'm going to get when IA is ripple free. Then we are going to get IA multiplied by pi minus alpha divided by pi square root in semi-converter, whereas IA itself in the case of full converter. And if I try to look at displacement power factor, I'm going to have cos of alpha divided by 2 as the displacement power factor in semi-converter case, whereas cos alpha is itself is going to be the displacement path factor, which is actually cosine of the angular displacement between zero crossing of the fundamental voltage and zero crossing of the fundamental current on the supply side. So this is going to be exactly the difference between the semi-converter and full converter. So if again, we want to write the transient equations, you should consider from alpha equal to omega t equal to alpha to omega t equal to pi. We are going to get the supply voltage being applied across the DC motor drive. So if I try to write transient equations or differential equations for the semi-converter. So we are going to have first from alpha to pi. We are going to have T1 and D4 conducting. And of course, supply is involved. So supply is on duty. So we generally call this as duty interval when the motor is getting a supply voltage. When the motor is getting a supply voltage, we have to write the equation as Vm sine omega t equal to RA plus LA DIA by dt plus EB, where EB is the back EMF. Now, under this condition, when we write the solution, we have to write the solution which is very, very similar to what we had done in the fully controlled converter case. IA of omega t is going to be two components which are corresponding to the particular integral. So one will correspond to Vm sine omega t, another one will correspond to EB. So we are going to get this as Vm divided by Z sine omega t minus phi minus EB divided by RA plus some K e power minus T by tau A. Just to reiterate whatever we said earlier, Z is going to be RA square plus omega square LA square root. Phi is going to be tan inverse of omega LA divided by RA. And tau A is going to be LA RA. And K can be solved for by using initial condition. Again, we are going to have IA of alpha equal to IA of pi plus alpha. But please note the differential equation which is written for pi to pi plus alpha is going to be different. It's not the same as what we have written here. This is the differential equation we have written during duty interval. Now, from pi to pi plus alpha, supply is not involved because it is freewheeling through T1 and D2. So it is going to be freewheeling, which means only the back EMF and stored energy in the inductance. Through that, the current is going to circulate. So under that condition, we call this as freewheeling interval. This is not duty interval. This is freewheeling interval. Already, whatever is the energy stored in the inductance, that is going to allow the circulation of current. So under this condition, there is no voltage applied across the armature. So 0 will be equal to RAIA plus LADIA by dt plus EB. And LADIA by dt in this particular case dia by dt is going to be negative. So this will be falling. The current will be falling. So this LA dia by dt will have a negative sign. So that is the one which is going to give the energy for the circulation of the current. So the stored energy in the inductance is actually given away. That is what is happening during this interval. So I should write this IA of omega t, maybe omega t dash. Let me say this is omega t dash. So this is omega t dash is equal to pi to pi plus alpha. Whereas I'm going to write here omega t is from alpha to pi. So if I try to write this, I should write this as minus EB divided by RA plus some k dash e power minus t by tau a. So this is the kind of current expression we are going to have, and k dash can be solved for by using the value of IA of pi from the previous interval. So whatever is at the end of the previous interval, that becomes the initial condition for the freewheeling interval. So there will be specifically two intervals that will be coming up in the case of this particular semi-converter operation. Hardly ever we will see discontinuous conduction because of the fact that there is no negative voltage at all. The negative voltage is completely absent. So the opposition to the current is really, really minimal. And that is the reason why we are going to have hardly ever any discontinuous conduction. So like what we wrote earlier, we can say EB equal to VA minus IARA. In this particular case, VA is going to be Vm divided by pi multiplied by 1 plus cos alpha minus IARA. That is going to be EB, which is K phi omega. So this omega is mechanical speed. So let me write this as omega m. So the mechanical speed of the motor is going to be Vm divided by pi k phi 1 plus cos alpha minus, and again we are going to write Te equal to k phi Ia, product of k phi and Ia. So I can write Ia to be Te divided by k phi, and one more k phi is coming from here. So k phi whole square multiplied by R. So this is the speed torque relationship for semi-converter. Whereas for full converter, we wrote a similar thing earlier, if you may recall, that was 2Vm divided by pi k phi cos alpha minus Te divided by k phi whole square multiplied by Re. So this is essentially full converter operation. So semi-converter, because there is no excursion in the negative side at all for the armature voltage, semi-converter will be able to give us only one quadrant of operation. It will not be able to give us even two quadrant like what the fully controlled converter gave us. This will give us only one quadrant of operation. So we will not be able to achieve regenerative braking in this particular case. But one good thing is we will always have only continuous conduction in all probability. Now to draw the speed torque characteristics for the semi-converter. Let us first of all compare this with the fully controlled converter. So for the fully controlled converter, we had this as the speed axis and this as the torque axis. And we said that at alpha equal to 0, if I'm going to have something like this is corresponding to alpha equal to 0. This is going to be alpha equal to 30. Maybe this is going to be alpha equal to 60. And I'm going to have something like this at alpha equal to 90. Then I'm going to have 120 and 150. I'm simply showing all of them. Now we also said no load speed for alpha ranging from 0 to 90 degrees. It is Vm divided by K5 for fully controlled converter. Whereas when alpha is greater than 90, we said omega no load is going to be Vm sine alpha divided by K5. This is what we said in the last class. So let me mention those points also in the characteristics. So if I say that if it had been supplied by a DC supply, it would have the no load speed would have come here 2 Vm by 5 K5. Whereas now the no load speed will be almost 1.5 times that. So I should show it somewhat like this. This is going to be Vm divided by K5. Now for alpha equal to 30 also it has to be joined with this. For alpha equal to 60 also it should be joined with that. And even for alpha equal to 90 it should be joined with that. But for alpha equal to 120, it will be Vm sine alpha, that is Vm sine 120, which will be about 0.866 times the original value. So let us say somewhere here. So this is going to be Vm sine 120 degrees divided by K5. So from here, I should try to join this to Vm sine 120. Similarly, I have to show it as though this is Vm sine 150 divided by K5. So this will be joined with the characteristics corresponding to alpha equal to 150. So these are going to be the no load speeds for different values of alpha. If I try to look at, this is all full converter. If I try to look at semi-converter versus full converter, Vm by divided by pi 1 plus cos alpha is for semi-converter, whereas 2Vm divided by pi cos alpha is for full converter. Both of them will be equal to each other at alpha equal to 0. At alpha equal to 0, both of them are going to be exactly one and the same. So I will have a similar characteristics exactly for semi-converter as well. So this is going to be semi, whereas this is going to be full. So both of them are going to exactly be one and the same for alpha equal to 0. They will not be different at all. But at alpha equal to 30, semi-converter will give me a higher voltage. So I will have essentially this lying above the fully controlled converter characteristics. So this is going to be for semi-converter alpha equal to 30. Then similarly at alpha equal to 60, I will have again lying even above. So the difference is going to keep on increasing. So this is going to be for alpha equal to 60 semi-controlled converter. So the semi-controlled converter for a given torque will offer a higher speed at a given alpha as compared to what is offered by the fully controlled converter. The fully controlled converter speed will be lower. This speed is lower. whereas we are going to have the speed to be higher for semi-controlled converter. Okay, so these are the speed torque characteristics for fully controlled converter and semi-controlled converter. So let us now try to work out a couple of numerical examples so that there is clarity in our understanding for the functioning of semi-controlled and fully controlled converters. So let us try to do a couple of numerical examples. The problem statement goes as follows. A 220 volts, 12 ampere, 1200 RPM, 2.2 kilowatt, separately excited DC motor drive has RA equal to, that is armature resistance equal to 0.9 ohm and armature inductance equal to 1.5 millihenry. It is fed by a fully controlled converter, or I can say full converter, single phase full converter, operating at a firing angle of 45 degrees while delivering rated torque. Calculate its speed. Assuming continuous conduction. Continuous conduction. Also obtain real power, reactive power, and displacement power factor on the supply side. Okay, so this is the problem that has been given. So let us try to solve this. First and foremost thing let's try to do is to convert this 1200 RPM into radians per second. So 1200 RPM is going to be 2 pi multiplied by 1200 divided by 60. That comes out to be 125.66 radians per second. So this is the speed in radians per second. And what is the back EMF at rated condition? Let's try to get that. So that is going to be 220 minus IARE. So IA rated value is 12 multiplied by 0.9. So VA minus IARE. So this comes out to be 209.2 volts. So I can definitely calculate K5, which is the back EMF constant. So this is K5 omega M. So K5, which is the back EMF constant, I can calculate as 209.2 divided by omega M. So this is 209.2 divided by 125.66. This comes out to be 1.665 volt second per radians. So this is the kind of back EMF constant we are getting. Now let us try to calculate corresponding to alpha equal to 45. What is the supply voltage? What is the DC motors armature voltage? Of course, the supply value is not given. Let us maybe that is missed out. So AC supply voltage is 230 volts, 50 hertz. So 230 volts obviously is RMS value. So we are going to say VA average is going to be 2 VM divided by pi cos alpha, assuming continuous conduction. So if we assume continuous conduction, this is how the voltage is going to be. So this is going to be 2 multiplied by 230 times root 2 divided by pi cos of 45 degrees. So this is going to be 2 multiplied by 230 root 2 divided by pi multiplied by 1 by root 2 because cos 45 is 1 by root 2. So I can cancel this and this. So this is going to be 460 divided by pi. And 460 divided by pi comes out to be 146.37 volts. Okay. Now, what we need to do is we have to calculate speed. So for calculating speed under this condition, we have to first of all write EB equal to VA minus IARA. That is 146.37 minus, because it is rated torque, IA is going to be IA rated and RA is 0.9. So 12 is IA rated, 0.9 is the armature resistance. So this is going to be 146.37 minus 10.8 volts. So that comes out to be 135.57 volts. Now we can calculate the speed at this condition. We can directly calculate this as 135.57 divided by K5 radians per second, assuming constant excitation. So K5 we got as 1.665. So I should be able to simply divide this 135.57 divided by 1.665. So this comes out to be a speed which is corresponding to 777 RPM, approximately 777 RPM. Or if you want it in radians per second, this comes out to be 81.42 radians per second. So this is 81.42 radians per second, or I should say 777.6 RP. Okay. Now we already derived what is the displacement power factor. Displacement power factor is same as cos alpha. If I assume ripple free current, of course. So I should say, assuming ripple free current, we can calculate what is RMS current, what is DPF, etc. So if we assume ripple-free current, so displacement power factor is going to be cos of 45 degrees, which is 1 by root 2. Similarly, we can calculate what is IRMS. IRMS will be same as IA average. And IA average in this particular case is 12 ampere. And VRMS is 230 volts. So we can calculate what is apparent power. So apparent power is going to be Vrms multiplied by IRMS, which will be 230 multiplied by 12. This is going to be S, apparent power. Okay, so 230 multiplied by 12 volt ampere. Now, real power is going to be S multiplied by cos 45 degrees. And reactive power is going to be S multiplied by sine 45 degrees. So this is going to be 230 multiplied by 12 divided by root 2. This will also be 230 multiplied by 12 divided by root 2. So this comes out to be 1951 watts. This will be 1951 VAR. So this actually tells us that 1950 watts are delivered to the motor when it is working at a firing angle of 45 degrees. And from that, we have to reduce whatever are the input losses, that is IA square RA losses within the motor. And only rest of it is going to be coming out as output, although the rating of the motor happens to be 2.2 kilowatt. So compared to 2.2 kilowatt, this is going to be definitely lower. So for example, if I try to say what is the actual output at this condition, then I should say 1951 minus IA square RA. So that is going to be 1951 minus 12 square multiplied by 0.9. This is going to be the overall power that is available. So this is 1951 minus 144 multiplied by 0.9. So that comes out to be 1821 watts. Approximately 1821 watts are the one that is coming out as output, although the original rating of the motor is 2200 watts. Let us try to do the same numerical example for semi-converter and compare the two. So let us say the same motor now is being fed by a semi-converter at a firing angle of 45 degrees. And we want to know what is the speed, what is the real power, what is the reactive power, and supply voltage is 230 volts, 50 hertz. So we had already calculated these things. Let me reiterate. EB at rated condition is 209.2 volts. And this is at rated condition. And K5 was 1.665 volt second per radian. And we already have been given that IA is 12 ampere and RA is 0.9 ohm. Now, the semi-converter is working at an alpha of 45 degrees. So that is Vm divided by pi multiplied by 1 plus cos alpha. This is going to be the average armature voltage. So this is 230 times root 2 divided by pi multiplied by 1 plus 1 by root 2. So this is the value of armature voltage, and that comes out to be 176.74 volts. Whereas if you had looked at what happened in the case of full converter, it was only 146.37 volts. So very clearly we are having a higher voltage, almost 30 volts higher than whatever was the full converter. So correspondingly, if we try to calculate the speed omega m at rated torque, that means rated IA. We can calculate this as VA minus IARA divided by K5. So that is going to be 176.74 minus 12 multiplied by 0.9. That will be the back EMF divided by 1.665. This is going to be the speed. And this speed comes out to be 99.66 radians per second, which is also incidentally 952 RPM approximately. So you are getting 952 RPM in this case, whereas it was 777.66 RPM in the previous case. That means the speed is definitely less. So that's what we drew here. The speed is going to be lower for a fully controlled converter, whereas it is going to be higher for a semi-controlled converter. Now, let us try to see what is DPF. So displacement power factor is going to be cos of alpha by 2. So that is cos of 22.5 degrees. So this is going to be the displacement power factor. So very clearly, this is going to be on the higher side as compared to cos of 45, because cos 22.5 is going to be definitely higher. And if we calculate RMS current on the supply side, assuming ripple-free IA. So that is going to come out as we calculated this, if you may recall, in the semi-converter case, what is the kind of RMS current we get? I think IA of root of pi minus alpha divided by pi. This is what we calculated, right? So let me use that expression directly. So that is going to be 12 multiplied by pi minus 45 degrees, which is pi by 4 divided by pi. So we are writing this as IA multiplied by pi minus alpha divided by pi, square root of that. So this is 12 multiplied by square root of 3 by 4. So this comes out to be 6 root 3 ampere. Okay, so this comes out to be 6 times root 3. So 6 multiplied by 1.732, and that comes out to be 10 point. This is 10.39 ampere. In the previous case, we got the RMS current to be 12 ampere itself, whereas here it is 10.39. So RMS current is definitely lower. So if I calculate apparent power in this particular case, we are going to have 230 multiplied by 10.39 volt ampere as the apparent power. And real power in this particular case, what we get is going to be 230 multiplied by 10.39 multiplied by cos of 22.5 5 degrees. So this turns out to be 2208 watts. So this comes out to be 2208 watts. Whereas if you actually look at what is the kind of power input that is going in fully controlled converter case, that is only 1951 watts. Whereas in this particular case, if I try to calculate what is the reactive power. So reactive power in this particular case, I can calculate this as sine of 22.5 multiplied by 230 multiplied by 10.39. Otherwise, I can say if this is S and this is P, and if I want Q, I should say S square minus P square, square root of that is going to be Q. And that comes out to be 914.7 VAR. So the reactive power is definitely much lower as compared to a fully controlled converter. So the fully controlled converter, generally the advantages you are going to have, it is going to be possible for you to have 2 quadrants of operation, whereas semi-controlled converter will deliver definitely more amount of real power. It will operate at a higher speed. There is a better possibility of continuous conduction. The reactive power consumption will be lower. All those things are advantages. But one of the major disadvantage is going to be you cannot get 2 quadrants of operation. That is not going to be possible. Okay. If we really want the power factor in these cases, if we want the power factor in these cases, the real power factor has to be calculated as displacement power factor multiplied by whatever is the fundamental component of current, supply current divided by RMS current. This has to be calculated as the power factor, and it's not going to be very easy for us to calculate the fundamental component of current, especially in the case of semi-converter. So at least you should know what is the methodology of calculating the power factor. That is the reason why I am giving this particular expression. Okay. So much so for single phase converter fed DC motor drive. So we will be looking at 3-phase converter fed DC motor drive in the next class. And after that, we will go over to the series motor drive, basically.